Right, thank you very much. So lots of bits of maths you study have equations and formulae and trigonometry and so on, but some bits of maths are completely free of equations, just about patterns. I want to talk about such a bit of maths. So we know equations in this talk at all. It's a part of maths that's called Ramsey Theory. And it's unusual in that it comes with its own pet philosophy. So it's all about one question. I'll write the question up now. It'll sound rather vague, nebulous, wishy-washy, but then we'll see some examples of what it actually means. And the basic question is, you've got some big amount of disorder, some disorderly mess. Can you find inside it a nice little patch of order? So the basic question is, can we find some order in lots of, let's say, in enough disorder? So some of you may have heard of chaos theory. This isn't that. Chaos theory is the opposite. Chaos is about how when you have an orderly system and some nice equations, a teeny change can lead to massive disorder later on. This is not. This is the opposite. This is about, in disorder, you have some order. OK, that sounds pretty vague and weird. Let me give you a concrete example. Suppose you've got 6 people in a room, and any 2 of them are either friends or strangers. And you assume nothing at all about the pattern of friends and strangers. So if A knows B and B knows C, then maybe A knows C, maybe doesn't know C. Okay? That's the disorder, the totally unknown pattern of friends and strangers among 6 people. What you'd like to find, if possible, is some order. And order is going to be, let's say, 3 people who all know each other or who are all strangers. Okay, so you'd like to find 3 people, A, B, and C, so that either A knows B and B knows C and A knows C, or A doesn't know B, A doesn't know C, B doesn't know C. Okay, so that's the question. Can you always do that? Is it always the case? Let me try and draw it as a picture. So let's have a dot for each person. So I have 6 dots. And to avoid writing the words friends and strangers, I have 2 colours of chalk. Let's say that red means is a friend of, and blue means stranger. Okay? So when I say there are 6 people, and every 2 are friends or strangers, that in the picture means you've got 6 dots, and every 2 dots joined by a line. Agreed? Red or blue? Let's have a go. Let's try it. So I'll just draw on every pair. Any old how. How are we doing? We're missing this line. And that looks about like everything. No, one more. That's everything. OK. That's our disorderly mess. Right? You've got 6 dots. Every 2 are joined by a red or blue line. OK. Now, what's our order? We want to find 3 people who are all friends or all strangers. Now, what does it mean to have 3 who are all friends? It means you've got 3 points joined by red, red, red. So like a red triangle. What does 3 strangers mean? It means blue, blue, blue. A blue triangle. So translating from people to the picture, here's what the question is. The question says, you take 6 dots, you join them up with red or blue. Is it always the case that however you've done that, be it with a pattern or with no pattern, is it always true that you can find somewhere in that picture a red triangle or a blue triangle? So in this example over here, I think, OK, there's a nice red triangle. So the answer was yes in that particular case. It so happens there's also a blue triangle. Right? This is a blue triangle down here. Obviously, it's very stupid to say, is it always true you've got a red triangle and a blue triangle? Because if I made every line red, there'd be no blue triangle. So that's why the question obviously doesn't say, is it always true there's a red and a blue triangle? The question is a triangle all of one colour. Okay? And that's an example of this question. The disorder is the unknown mess of colouring. The order is a nice pattern. Okay, so we try an example, we find yes, the example was true. Perhaps we try 2 more examples, find it's true again. But of course, we'd like to be certain it's true. We would like to prove it. Prove meaning have some logical reason it makes it certain it's true. After all, perhaps you try 10 examples that's true every time. For all you know, your 11th will be some horrible, messy example of colouring where you don't find a triangle of one colour. So what could you do? You could say put it on a computer, which of course you could. There are quite a lot of ways to colour 6 points. There are about 32,000 ways to colour it in. So you wouldn't want to do it by hand, but of course a computer in a few seconds for you. And just believe me, the answer is yes. If you try all 32,000 cases, you'll find it always is true there's a nice triangle of one colour. So the answer is yes. But that's very unsatisfactory, because actually you prove things for 2 reasons. One is to be sure they're true. Yep, that would work. The other is to understand why they're true. Can you tell your friend what made it true? And I think saying, here's a big computer printout with 32,000 ticks isn't very satisfying. Or put another way, suppose you've done that, and your friend says, is it true? You'd say yes. They'd say why. You'd say, oh, believe me, I've checked it. That isn't good. You want to prove in a way to convince your friend it's definitely true. Okay, so let's have a go at proving this. Before we do, you might ask yourself the question, why did I say 6? Right? Why did I say 6 people? Why not say 5 people? It's a nice question about 6. Why didn't the question say, given 5 people, can you always find 3 of your friends or strangers? And the answer is that for 5, it's just not true. So here's an example with 5. So when I say not true, I mean there is a bad way to colour. So there's an unpleasant, evil way to colour these in such a way you don't have a red triangle or a blue triangle. And it's actually quite nice. You imagine you're 5 people sitting around a pentagonal table, and you say to your neighbours on either side, your friends, so left and right you know them, and across the table you're strangers. So that would mean in a picture, I'd go around the outside in red, and on the inside in blue. And if you think about it for a second, there's no red triangle. Well, that's pretty obvious. There's no blue triangle either, because the blues are also just a pentagon, aren't they? Or a pentagram, whatever it's called. Okay, so that, by the way, is also a cautionary tale. That's the only way to colour without a red or blue triangle. So if you tried some examples by hand, unless you stumble on that exact example, you'd try 20 examples, you'd be sure it was true, and you'd be wrong. Anyway, back to 6. So we'd like to see why this is always true. We'd like to do it by someone that doesn't say, write down 32,000 cases. So there's a very nice argument which goes as follows. Let's just focus on one point. So think about one person. Okay. Now, out of that point come 5 lines, agreed? There are 5 other people. If I give you 5 lines, there can't just be 2 red and 2 blue, because 2 and 2 is less than 5. So if I give you 5 lines, they've got to be 3 or more of one colour, right? So let's suppose there are 3 or more red ones. So I shall focus on those. So we have 3 red lines to 3 other points. I'll ignore the other 2 points. If there are more than 3 red, I don't care to take those 3. Okay? Again, we know we either get 3 red or 3 blue. So I'll have a later case to consider, which is the case of my point having 3 blue. Okay, back to this. So I've got a point with 3 reds, a person with 3 friends. Now, how about those 2 points? If they're joined by red, we're done, aren't we? We've got a red triangle. Finished. So our only problem is if that line is blue. Otherwise, we're done. How about those 2? If they're joined by red, we're done, red triangle. So our only problem case is when they're blue. And how about those two? Again, if they're joined by red, we've got a nice red triangle. So the only problem case is when they're blue. Aha, that's a blue triangle. We're done. In this case, actually, it's the same by symmetry, isn't it? There's nothing special about the word red or the word blue. Whatever I said in the red case with blue lines, I did in the blue case with red lines. Right? If any of those lines are blue, we're done, blue triangle. If they're all red, red triangle. Okay, so there we are. Hope you agree that's something you could tell your friend in less than 10 minutes, like in about 1 minute. And it was totally convincing. It certainly beats those 2,000 cases. Okay, so that's our first example of Ramsey theory. We've shown in enough disorder, i.e. 6 points, you can find a little teeny patch of order, a triangle all of one colour. Okay, so what would be the next thing to ask? You'd say, let's find a bit more order. Let's find not 3 points all joined by red or blue, but 4 points all joined by red or blue. Right, that's the next thing to ask, obviously. So how about finding either 4 points all joined by red or 4 points all joined by blue? Right? Can we do that? If you have, so in terms of people, is it true if you have 10 people in a room, there are some 4 who are all friends or all strangers? If 10 doesn't work, maybe 20 is enough. Is it true with 20 people? Is it true with 1,000 people even? Maybe there's no number that works. Maybe I can find you a horrible configuration of 1 million people in such a way, I've drawn a pattern of friends and strangers among these 1 million people, so that there's no 4 who all know each other and 4 who all don't know each other. That could be the case. It's not clear at all. You might guess 6 is double 3, so maybe the answer is 8, but that's just a guess, and you wouldn't be able to do anything with it. Okay, so that's our task. Everyone clear on the task? The question is there some number of points so that whenever you join up with red and blue, you always guarantee to find a red 4 or a blue 4? Or again, or in people terms, is it true if 100 people in a room, you can always find either 4 who are all mutual friends or 4 who are all mutual strangers? So it turns out that that's too hard a problem to try and do straight away. If you try and draw pictures like this, you end up with case 1, case 2, subcase 1a, subcase 1b. It explodes exponentially, it gets nowhere. So it turns out this is the wrong thing to ask. It turns out this is too complicated. It's best to go for a kind of halfway house. So we know it's true you can find a red or blue triangle, a red 3 or a blue 3. We're going for red 4 or blue 4, and it turns out the key idea is to say, let's go for the halfway in between. Let's go for a red 3 or a blue 4. So we're breaking the symmetry of the colours, but 3, 4 is sort of halfway between 3, 3 and 4, 4. So we're going to go for either a red triangle versus or a blue 4. And it'll turn out, as we'll see, that once we're experts on that, that will be the building block we need to get to 4, 4 eventually. Okay, so let's have a go at this. Again, I don't really care exactly what number. I just don't know some number of people's enough. Like before 6 was enough, we said, by the way, 5 isn't enough. The key thing was that some number was enough disorder. So here, I'm not terribly concerned about how many people you need, but I'm concerned that it's possible eventually. So let me show you a nice argument that 10 is enough, 10 people. You're allowed to say, why 10? You'll see in a second why 10 comes in. Okay. So let's have 10 points. So I'm going to show you now why it's always true that if you have 10 people in a room, you can always find 3 friends or 4 strangers. Okay? Or in the picture world, I'm saying you have 10 dots, all joined up with lines. The claim is you can always find a red triangle, a red 3, or a blue 4. And you'll see during this why I chose 10. Okay, so let's try and copy what we did before. Let's try and say, focus on one point and the 9 lines out of it. Okay, so let's pick one. So our unpleasant opponent has given us some nasty colouring of the 10 lines of 10 points. It's our job to find a red 3 or blue 4. Okay, so let's focus on one point. Out of that point come 9 lines because there are 9 other points. Nine lines. Now, those lines have certain colours. Before, we said, in the previous case, we said we have 5 lines, so we have at least 3 of one colour, didn't we? Because otherwise, 2 and 2 is less than 5. Here I want to say, must have at least 4 red or at least 6 blue. That is correct, isn't it? If you didn't have 4 red and didn't have 6 blue, you'd have 3 of those and 5 of those, which makes only 8, right? And 8's less than 9. So those must be true, right? If you have 9 objects, and each object is red or blue, you couldn't have only 3 red, only 5 blue. That wouldn't be enough objects. So either 4 or more red or 6 or more blue. Again, why have I chosen 4, 6 rather than 5, 5? You'll see in a minute. Okay, so we've got 2 cases to look at. Let's try the case of at least 4 red and see what happens there. So we've got a point joined by red to 4 or more other points. Let's focus just on those 4 points. Okay, I'm trying to copy the knowledge we built up from the previous proof. So let's have a go. Right. Between those points, what do we see? If we see any red line, we're done, aren't we? Right? Any red line I draw, like that one, makes a red triangle. And we're done. Right? A red triangle is success, remember? So red triangle is good. So any line there that's red is good. So I mustn't draw, the only problem case is nothing red there, but then they're all blue. And if all these are blue, so this is blue, or else we've got a red triangle, that's blue or else red triangle, same for that, same for that, same for that, same for that. Oh, that's a red 4, it's a blue 4, we're done. Right? Blue 4. So what we're saying is, by looking between those 4, we either see some red line somewhere, red triangle, end of story, or we see everything blue, that's a blue 4, we're done. So that case is fine. I hope you agree that is awfully similar to the previous problem, isn't it? Okay, good. So far, so good. On to the next case. At least 6 blue. So again, I'll focus just on the point and its 6 blues. I'll ignore the other points. So we've got a point here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, off we go. Is there a blue line between those 2? Well, actually, there could be. Right? If there's a blue line there, we get a blue triangle. But so what? We're going for a blue 4. Right? We're itching to say, aha, if that's blue, we're done, so the only problem is if it's red. But that's blue, we're not done. Going for a blue 4. So actually, it's not clear what we do now. What do we do now? So you've got this point joined by 6 lines to those 6. I want to use something from earlier. The method from earlier isn't helping us much, right? The method from earlier, it says if any line's red, we're done, if all blue, we're done, was great in that case, but here it's not going anywhere. So can anyone see what we should say now? Okay, let me do it like this. Think about those 6 points. Forget this one, just focus on those 6 points. What do we know we always get among 6 points? Our previous theorem says whenever you have 6 points, you always have a red or blue triangle, right? Or in terms of people, focus on these 6 people, we know, whatever else is happening in the room, among any 6 people there's a red or blue triangle. So we'll apply our previous result. Amongst these 6, we know there must be a red triangle or a blue triangle. Oh, that's why I chose 6, by the way. Okay. If there's a red triangle in those, say it's like that, we're done. A red triangle is a red triangle. Success. So that case is easy. There's a blue triangle amongst those 6. We're also done because those 3, the triangle, with Mr. Starting Point, make a blue 4. So we're done. That would have been impossibly hard if we hadn't done the case of red and blue triangle first with 6. If we'd started off today with 3 of this thing, there would have been no chance. So we used our earlier work. Great, so we're done. And that's where the 10 came from. So we need to have 6 blue to apply our previous result. We certainly need 4 red, so we could say amongst those 4, if any 2 are red, we're done. If they're all blue, we're done. So I need 6, 4. So I need to be able to say, when you look at lines out of a point, we don't have a 3-5 split. So I need more than 8 lines out of a point. That's where the 9 came from. That's why it was 10. Okay, great. That's very nice. So we now know that we can answer our halfway house question. Right? We now know that amongst any 10 people, you can always find 3 friends or 4 strangers, which is a good halfway thing to do. Just by the way, you might say, is 10, can you improve on the 10? Like in the earlier thing, we did it with 6, and we knew we couldn't do it with 5. So you might say, can you improve on the 10? Suppose I only had 9 people. Might it still be true? You always find a red 3 or blue 4. Well, obviously it's going to be no, right? Because we needed the 4 and the 6, didn't we? So this would not have worked with 1 less person, this proof. That doesn't tell you the result isn't true for 9. It just says this proof wouldn't work for 9. Now, it's pretty obvious you are going to need it because we know with 6 you have this problem. But weirdly, it is true for 9. So there's a digress from the main theme by showing you actually, although this is tailor-made for 10 and can't work for less, it does work for less. So we try and do 9. Let me show you that, like, very, very strange that 9 is also enough. I'll rub this off. So given 9 points, let's try and copy the previous proof. It's going to fail, right? Because it's not true that 3 and 5 is less than 8. But still, let's check and see why it fails. Okay, so pick a point. Out of it come how many lines? Well, 8 lines, right? We've got 9 points. Our opponents coloured them up, so with 8 lines out of it. There are 8 lines out of it. Okay, what do we know? We know, from what I just erased from the board, that if we're lucky enough to have at least 4 red lines, we're done. Agreed? So if at least 4 red, then we're done, aren't we? Right? If 4 of those are red, That was the case we just did. We said, look at the 4 endpoints. That's what we did before. And equally, just like before, it's still true that if at least 6 are blue, then again, we're done for the same reason, right? But unfortunately, you can't say, oh, by adding up the numbers, there are at least 4 red, at least 6 blue, because we only have 8 lines, and sadly, they could be 3, 5, couldn't they? Right? If it's not a 3, 5 set, we're done. If it was only 2 red, 6 blue, great. 4 of each is great, but there's a 3, 5 split. And they could. You can, obviously, if I said to you, please draw out of a line 3 red and 5 blue, you can do that. And there's no contradiction in that. So sadly, we're not done. And here's our problem case. Our problem case, our bad case for us, is when out of our point we have exactly 3 red and exactly 5 blue. And then we're not, then we're in trouble. Okay. Actually, stepping back for a second, we start that by saying pick one point out of the 8 lines. Actually, if there was any point anywhere that didn't have a 3, 5 split, we'd be done, wouldn't we? Right? If I can find you a different starting point to the 9, out of which there were 2 red, 6 blue, we're happy, aren't we? Yep. So the only problem case for us is the case where, for each of our 9 points, is annoying 3, 5 split. Let me try and draw that. This is our only problem case. So we've got 9 points. And out of each, we have exactly a 3, 5 split. So I have 3 red from here, 3 red from here, and so on. So out of each, we see 3 red lines okay. If that isn't the case with that, there's even one solitary point out of which the 8 lines don't go 3 red, 5 blue, we're done, aren't we? So we either get 6 blue or more, or 4 red or more. But that's our problem case. In that case, our proof isn't working. If you try and draw it, you'll find this actually can't happen. Why not? So there's a reason why it is impossible to draw a picture of 9 dots, all joined by lines, in such a way that out of each point come exactly 3 red. Why is that impossible?
Is it because if you've got each point with 5 coming out of it, there can be more blue possible, so there can be multiple blue going into some point. Because you've got 9 points with 5 blue lines, you can have 45 blue lines, which is more than you can actually fit in there.
If I did have 5 blue out of each point, how many blue lines are there?
45.
You sure? You're on exactly the right lines. If out of each point come 5 blues, how many blue lines are there? Right. That's right. If you think about it, each blue line's got 2 ends, hasn't it? Right? If I draw a picture which contains 6 blue lines, they've got 12 blue ends. Now, if you have, out of each point, 5 blue lines, then very good. You have 45 ends of lines. So you have 22.5 blue lines, which is difficult. So that can't happen. Right? You'd have 45 ends of blue lines, because each point has got 5 ends of blue lines. There are 9 lines. That's 45. So number of blue lines. There are 9 people. Each one has 5 blue lines out of it. but we've doubly counted it, right? Every line has got two ends, so you'd have to halve that number of blue lines, and you would get 22.5 blue lines, which is difficult. So actually that can't happen. So that's really weird. It's so obvious from the proof of 10 that 9 isn't enough, but actually 9 is enough, because in the one problem case, for a weird, odd, even reason, that problem case can't happen. Okay, that's quite nice to know. Okay, you'd bet a lot of money this proof doesn't work for 8 points, and you'd be right. So let's be sure that 8 doesn't work. So like with the 5 example of red and blue triangle, to convince you that 8 points isn't enough to get a red 3 or blue 4, I can't just say, oh, that proof didn't work. Maybe a better proof works. After all, for 10, the proof didn't work, but a better proof worked for 9. So to convince you it doesn't work for 8, I've got to give you a counterexample. I've got to give you a bad colouring. Right? I've got to draw you a picture, like that pentagram thing. I've got to draw a picture of 8 points with lines with no blue 4 and no red 3. Let me do that now. So 8 points. The answer is no. So we try and draw a picture. So I'll try and draw 8 points sort of around a circle. And I'll tell you, okay, I can't draw. I'll draw the reds. I'll leave the blues undrawn. So we're going to go around the outside in red. So it's an octagon thingy. And I'll also draw a red line from each point to its exact opposite point across the diameter, okay? So this point is joined to that one, this is joined to that one, this is joined to that, that's joined to that. And everything else is blue. So if you like, around the circle, your neighbour with the opposite point, that's red. 2 away or 3 away is blue. Now, it's completely obvious there's no red triangle there, right? You can't have a red triangle even with the diameters. There's also no blue 4. All that's saying is, if I give you 4 points on here, well, if 2 are adjacent around the circle, that's a red. So I've got to have 4 points around the circle, no 2 adjacent. If you think for 5 seconds, that means they're all 2 apart. They go in steps of 2, don't they? And if they go in steps of 2, then the opposite ones are 4 apart. Isn't allowed, right? I go 2, 2, 2, 2, but then those 2 are joined by red, not by blue. So it can't be done. I think that's not super surprising. Given how close we were to failing our proof for 9, it's not very surprising that 8 worked. Okay, where are we? We've done our halfway house goal. We've shown there is a number that works for red 3 or blue 4, which was 10, or even better 9. And I promised you that will be the key we need to build with to get our real thing of 4, 4. So let's now do 4, 4. So we're now on to our 4, 4 case. So we're going for blue 4 versus red 4. I'm going to claim that 18 points works. And again, you'll see where 18 came from in a second. So if you like, in terms of people, I'm claiming if you have a class of 18 people, you'll always find in it 4 who are mutual friends or 4 mutual strangers. Again, a bigger patch of order, of course, in a lot more disorder. Okay. Why 18? You see in a second. Pick a point. So I'm doing the usual proof where we're doing our counting lines and so on. And we're going to try and use our earlier work like we did before. Okay, out of that point comes 17 lines, right? Because there are 17 other people. Okay, if you have 17 objects, you can't have only 8 red, only 8 blue, because it only adds up to 16. So it's certain you've got at least 9 of one colour. Have at least 9 red, or at least 9 blue. Let's do this case first. Of course, by symmetry, it'll be the same as the other case. I'll do this case. So let's do the case of at least 9 red. Let's see how we draw a picture. We have a point here. We have 9 points here, and all lines are red to there. Okay, that's our picture. So we've got a nice point here. We've got 9 things there, and those are all red. And our job is to find a red 4 or a blue 4. Okay. And as always, we're not going to get away with our thing at the start of the step. We can't just say, if a line is red, oh, look, we're done. Because if a line's red, we just get a red triangle, which is, who cares? We're going for a red 4. So what do we say? We say, well, amongst those 9, what's a fact we know about 9 points? Yeah, that's right. We just proved that whenever you have 9 points, you always have a red triangle or a blue 4, right? So here are 9 points. We know in any collection of 9 points anywhere in the universe, you can always find a red 3 or blue 4. So in here we have either a red 3 or a blue 4. Is that good for us? Yes. A red 3 in here with that makes a 4, doesn't it? All right? And remember, these are all friends of that guy. So if these are mutual friends, that's 4 friends. So if it's a red triangle, we're done with that, making 4. And if it's a blue 4, well, that's a blue 4, we're done. So we're done. And we use the case of 3, 4 on the way. Which is, it's so weird because somehow our starter problem was triangle, triangle. That's symmetry in red and blue. Our ending thing was 4, 4, symmetric. But we had to go via this halfway house and asymmetrical thing. Okay. Does 17 points work? It doesn't, but I'm not going to draw you the picture. So there's some horrible picture you can draw where you look at it with a microscope or something and you find that there's no red 4, no blue 4. So actually 18 is the right answer. Okay, what next? Obviously, you'd want to go up in level and ask for some more order, like a red or blue 5. Again, I don't really care if it's 1 million people you need. I just know there's some number that works. So let's just end by thinking how that would go. So in terms of a picture, how did we do the case of 4, 4? So if I write 4, 4, by that I mean a number of people that guarantees red 4 or blue 4. Now, that came from our earlier work on 4, 3, didn't it? I guess officially, since we did the red and the blue, there's 2 cases, I used the earlier theorem that says there's always a red 3 or a blue 4 amongst 9, and also always a red 4 or blue 3, but by symmetry. So this came from knowing about 3, 4, and about 4, 3. Now, where did our 3, 4 come from? If you think back, we did 3, 4, we used our 3, 3, didn't we, on the way? And actually, if you think about it, we also used, in a kind of pretentious CUD way, 2, 4. 2, 4 is a very silly... What is the 2, 4 question? 2, 4 says, is there a number of people so that with that many people in a room, you can always find 2 who are friends or 4 who are all strangers? Well, that's kind of silly, because if any 2 are friends, they're friends, otherwise they're all strangers. So 4 people is enough, right? This is like saying, if I give you 4 dots and lines between them, you either have a red line or it's all blue. But that is what we used in that case, in fact. So that came from those 2. This was trivial, this we did by hand. And similarly, 4, 3 comes from 3, 3 and 4, 2. So actually, each time we did something, it always came from 1 less and 1 less. That's always how it worked. We always said, take a point, out of it come loads of red, So if in what's left we find a blue that's what we want, we're done, or a red of one less, we're done. That's how just now we said a red triangle, our initial point is a blue. So that picture has to do 5, 5. So to do 5, 5, what would you need to know? Doing directly no chance, you'd need to know 4, 5 and 5, 4. We don't know those, unfortunately. How would you do 4, 5? You'd need to know 3, 5 and 4, 4. And similarly here, you need to know 4, 4 and 5, 3. This one we know, we tick that one, we know that's true. 3, 5, how would you do 3, 5? Well, we haven't done that one yet, have we? You would need to know 2, 5 and 3, 4. This one we know, we've done that one, and that's trivial. 2, 5 is just 5. So we're done. And it always works like that. If you think about it, you keep bubbling down, you always bubble down either things you know at the end or to things with 2 components which are trivial. So that's it. And that's called Ramsey's theorem. So it's sort of saying that complete disorder is impossible. We always find some order inside it. Now, my last minute, I'll just mention one thing. For 4, 4, I said it was 18, and I said 18 is the right answer, 17 doesn't work. I didn't draw a picture for 17. For 3, 3, it was 6, we drew a picture for 5. For 5, 5, what's the right number? It's known to be between 43 and 49, but no one knows the right number. That's actually an open problem. It's completely amazing. No one actually knows the right number of points that guarantee red or blue 5. It's known if you have 49 points, yes, you always get it. It's known there's a disgusting picture on 42 points that doesn't have a 5, but no one knows where it's in between. You might say, how can that be? How can people not, mathematicians are quite clever, why haven't they solved it? It's because you're sort of asking exactly how much disorder do you need to get a certain piece of order. And by its very nature, disorder you can't characterize exactly. So a mathematician called Paul Erdős, who invented a lot of this, he had the following quote. He said, supposing an alien spacecraft arrived above the Earth and said to the Earth, you have 1 year to work out the value for 5, 5, or Earth will be destroyed. What should you do? You should gather all the mathematicians of the world in one place, link all the world's computers, work non-stop, hope for a breakthrough, hope to solve this exactly in a year. However, he says, if the alien spacecraft says you have a year to work out 6, 6, then that's so hopeless, you should spend your year working out how to destroy the spacecraft. And I'll stop there.